Hello, everyone, and thank you for joining me in today's episode of Caserta's Data Intelligence Webinar series. I'm your host, Remy Rosenbaum. Today, we're going to explore the topic of alternative data. Now, usually when I talk about alternative data, it's in the context of an indicator that discretionary investors and fund managers are using as a tool to outperform the market and generate alpha. But the use cases and impact of alternative data are not confined to the financial services industry. Just this week, I was at the Gartner Data and Analytics Summit in Orlando. And during the opening keynote, they had distinguished VP analyst Donald Feinberg. And he told this story about a domestic beverage manufacturer that was using alternative data from Asia in order to better forecast goods sold and reduce cost of overstocked inventory, translating into many multi-millions of dollars. In the insurance industry, alternative data is revolutionizing risk analysis and assessment. And soon, alternative data will become an integral part of the understanding of the larger data story in every industry. Today, we're going to focus mainly on alternative data in the financial services industry. 2 weeks ago, I was at Quandl's Alternative Data Summit in New York. Some of you might have been there. And after chatting all day with hedge funds and discretionary investors, it was crystal clear that a lot of these firms are struggling to realize their alternative data business goals and really incorporate alternative data into their trading strategies. Common challenges I heard included incorporating additional unstructured data sources, building out data pipelines, scaling up the platform, and having architectures too brittle to handle data schema shifts. Many of these firms don't have the internal resources to support alternative data and are falling behind while others rise to the top and outperform the market. In this episode, we're going to give you solutions to those challenges of architecting for alternative data. Our expert presenter, Robert Piccone, will explore how Caserta architected and built a scalable cloud-based analytics platform that includes both alternative and traditional data for a large hedge fund client of ours. Robert's been designing, developing, implementing, leading, and managing solutions in the realms of data science, analytics, and data warehousing for more than 17 years. He's a graduate of Columbia University's MS program in data science. He's going to be a great presenter. First, just a little housekeeping, and then we'll get started. Caserta, for those of you who don't already know, is a strategic consulting firm focused on data and analytics. We help business and IT leaders, just like you, transform their organizations by and through their data. We provide strategic consulting with detailed roadmaps, architectural design, and advanced implementation of our recommendations. Our expert consultants are force multipliers for our clients that partner with you to achieve your business outcomes and future-proof your business. This webinar today and other webinars that we produce, we do them to give you insight into today's hottest technological trends and issues. So after the webinar, I encourage you to speak with me about any questions you have on how to apply what you've learned today at your organization. Our initial consultations are always free, and if we do find an opportunity to work together, then we can discuss the next steps. And if not, we'll gladly point you in the right direction. If you're wondering, after the webinar, we will send you a recording to the email address that you provided. And if you have any questions throughout the presentation, please enter them in the questions panel on the right side, and we'll answer them during the Q&A session at the end of the webinar. Robert, the stage is yours.
Okay, great. So let's start with the recursive definition of alternative data. So alternative data is any data set that's an alternative to the traditional or primary data sets on which investment or trading decisions are made. Traditional or primary data is typically made up of publicly reported financial performance metrics, such as a firm's actual revenue, profit, earnings per share, growth forecasts, and reported investment flows into and out of a firm. In other words, the quantity of shares bought and sold by company insiders and large institutions. Sorry, I seem to have a bit of a lag on my presentation. Here we go. Sorry about that. Okay, so now that we know what alternative data isn't, let's define what it actually is. Alternative data is any data set that's used to infer or form a hypothesis on a firm's relative or absolute performance in advance of those performance metrics being reported or possibly even known by the firm itself. The data sources may already live in the wild, so to speak, on the public-facing internet, or it may be proprietary data available for purchase. Some examples of proprietary alternative data include transaction data from credit and debit cards, or retail loyalty reward programs, social media usage metrics, or even satellite photo data of retailer parking lots. Publicly available data is often purchased through a data provider that provides other services such as gathering, delivering, cleansing, and structuring the data. And so there's often a make or do-it-yourself versus buy decision involved with these publicly available alternative data sets. A good illustration of this is provisioning retailer website data as an alternative data source. The web pages themselves are, of course, freely accessible to anyone with an internet connection, but to harvest the data, you have to design and implement two functions. First, you need a web crawl process that traverses through the entire set of HTML documents that make up the site and saves the timestamped collection of HTML files. And second, you need a process that extracts all of the desired data points from the raw HTML data. So you basically have three different degrees to which you can do this yourself. You can go for the full do-it-yourself option and develop and manage both pieces of functionality. You can buy part of the functionality whereby a data vendor would perform the first function and periodically deliver to you a complete set of raw HTML files. Or you could buy both functions, whereby a data vendor would not only perform the web crawl, but would also distill the HTML data into specified data metrics, and then deliver a structured file containing those metrics. An important thing to consider in this decision is that even when both of these functionalities may be built into your platform, there may be other factors that make it beneficial to outsource those functions to a data vendor. Like your corporate network's browsing bandwidth and the sharing of data quality responsibilities with the data vendor are just two examples of this. And another thing to point out, as long as we're on this topic, is that even if you're buying exclusively pre-digested and structured alternative data from a vendor, it doesn't really negate the need for a fully built-out alternative data platform, since you still need to have these things, such as a unified data warehouse, an analytics engine, and a data laboratory environment to make use of that data. It's also worth pointing out that the quality of purchased data can vary wildly depending on the data set and the vendor, and that's why I use the term sharing of data quality responsibilities as opposed to totally outsourcing them. Okay, so now that we've spoken a little bit about the data itself, let's move on to the core requirements that an alternative data platform needs to fulfill. So it needs to be able to continuously ingest any number of raw data sources of any size, volume, or structure. So that's multiple file formats, structured, semi-structured, and unstructured, large quantities of small data files, large quantities of large data files, and so on. It also needs to be able to rapidly onboard new data sources. It needs to enable discovery and hypothesis testing on ingested data in order to create and refine use cases based on some subset of the available data. And in this context, when I say use case, I mean a specific investment or trading thesis based on some subset of your alternative data-derived performance metrics. So something along the lines of, when this trend is observed with this subset of data, that implies rising sales for firm X. So it also needs to be able to productionalize the preparation of newly ingested data towards all established use cases and rapidly deploy new use cases. And finally, it needs to be able to update a visualization layer that enables analysis and real-time tracking of the use cases. So what are some of the challenges in meeting these requirements? So one challenge is onboarding and enabling new data sources with minimal effort. In other words, you want to avoid the need for additional development or code refactoring to accommodate something unforeseen in a new data source that you want to onboard. Another challenge is the creation of universal data extraction processes. And what I mean by that is that an extraction process has to be capable of extracting all data points that are contained within a given file format, not reliant on a hard-coded schema for each individual data source, at least not for the ingestion, storage, or exploration functions. Accommodating schema shifts in the source data is another challenge, particularly with unstructured or self-gathered public data sets. And finally, scalability and the avoidance of bottlenecks is a common challenge. You want to be able to digest and process each individual data source in a timely manner, as well as be able to accomplish this in parallel on different data sources that will be landed at the same time. So this is an architecture diagram of an actual alternative data platform that we built out at Caserta for a large hedge fund client that addresses all of the aforementioned requirements and challenges. This particular reference project was done using AWS cloud infrastructure, so you'll hear some references to AWS-specific products like S3 buckets and SQS, but the design is agnostic with respect to the cloud service provider, as each piece of functionality has an equivalent product or service between Amazon, Google, and Microsoft's cloud offerings. With that said, so the platform encompasses 5 high-level functionalities. So we have the pipeline sequential steps of data ingest, compute, and serve. We have process monitoring and alert generation, and we have the overall orchestration process that choreographs the sequence of events that begin when new data is landed. So walking through the actual data pipeline steps, we have a number of data file formats coming in from a number of different data sources. Each unique data provider has its own designated S3 bucket, which is the landing zone and ingress point into our platform. Data can either be pushed to its landing bucket as soon as it becomes available, or it may be pulled via an API request and placed in its landing bucket on a schedule. The appearance of new data in a landing bucket triggers the ingestion and data quality check process, which removes the data from its landing bucket and archives it in the platform's archive data S3 bucket, which stores all data received at full fidelity in its original file format. From there, the extract and structure process runs on the new data, assuming it has passed its data quality check, which pulls all identifiable data points from the landed data and appends it to the structured data S3 bucket in Parquet format. From there, a curation process runs that prepares the structured data for use case-driven presentation and writes the curated data to the curated data S3 bucket, which is also in Parquet format. A query engine, which in this particular project case is Redshift Spectrum, sits on top of the curated data store and serves data visualization tools such as Tableau and MicroStrategy, where interactive use case tracking reports live. So the code base for all 3 of the processes that I just walked through is all written in PySpark, and it lives in and is executed from modular Databricks notebooks. Similarly, the alerts and monitoring functionality is also a PySpark Databricks notebook paradigm. And finally, Airflow is used to choreograph the entire dance of multiple data sources arriving at different and potentially overlapping times, whether scheduled or unscheduled. And then we have SQS used as the message queuing service that kind of stitches the steps of the pipeline together. So the platform has a few different audiences that will each interact with the platform in different ways with their own particular set of activities. Data analysts will be interacting with the curated visualized data to track and interpret ongoing use case results. This will happen primarily through the interactive reports that have been set up in visualization tools such as Tableau or MicroStrategy. But this may also involve direct querying of the curated data using the query engine. The data analysts, of course, report their findings to investment decision makers, and they also provide feedback to data scientists, suggesting useful additions and changes to the curated metrics that would enhance the use case or speed up the human analysis and interpretation process. As for the data scientists, they'll be interacting with the structured data store to perform data discovery, to test investment hypotheses, and periodically re-back test the established use cases. They'll do so using their own Databricks notebooks, which provide a powerful, scalable, and function-rich data laboratory environment. The data scientists also will add or modify the configuration settings of the curated data layer based on newly established use cases or from analyst feedback. And on that note, so ideally as a best business practice, you'd have an ongoing cross-pollination of ideas between the data scientists and the data analysts. So for example, the analysts would be communicating any gaps in the types of metrics being displayed, or maybe even come up with a metric wish list, which the data scientists would then take to perform a guided data discovery exercise to see if the requested metrics are present in the extracted structured data. Conversely, a data scientist could perform an unguided data discovery and present the data analyst with a menu of available metrics to the data analyst, and they could collaboratively assess the utility of those metrics and how they should logically fit into the curated data if they're worth adding. So let me throw out an example of the kind of collaborative activities that could be happening between data scientists and analysts. To reuse the example of online retailer website data, an analyst may observe some useful metrics while physically looking at the website with human eyes. The universal HTML data extraction process captures all identifiable key value pairs, but the key names found in the raw HTML will not always be obvious. So the data scientist might need some examples of the values themselves, particularly across a time series, in order to locate the name data structure containing the desired metric. Data engineers, be they in-house or contracted, implement the original pipeline and platform. And then your in-house data administrators and engineers would respond to and address data quality alerts and onboard new data sources. Data onboarding consists of creating a new landing S3 bucket if the data is provided by a new vendor, establishing a pull mechanism for the data if the new data is not going to be pushed, and updating the configuration data that guides the ingestion process. And on the topic of configuration data, all platform functionality is configuration driven. So the ingest, compute, and curate functions reference standardized configuration data. The onboarding of new data sources and additions or changes to how data sources are quality checked or curated are all accomplished through the modification of the configuration data. The configuration data includes as-of-date values to accommodate source data schema shifts. The point to making everything configuration-driven is that existing pipeline code base should never require modification. The code base is logically segmented and executed from distinct Databricks notebooks written in PySpark that mirror their modular functionality. In this manner, extension of new functionalities, such as universally extracting all data from a new file format type, is accomplished via the addition of a new code notebook, which is itself then designated as the extraction function for that file format in the configuration data. Okay, so let's zoom in a little bit on the configuration data that drives the main segments of the pipeline, and also go into a little bit more detail on the process that's going on within each segment, starting with the ingest. So ingestion configuration data contains the parameters required to ingest each distinct data source and perform its respective data quality check. Some primary examples include the file landing location, the file format, any required fields, any data type expectations, and the file naming convention. The ingestion process performs the configuration-driven data quality checks on any data that lands in any of the specified landing locations and moves that data to the archive bucket. The data is archived at full fidelity with a key naming convention that encodes the file's data source, its ingestion date, and whether the file passed or failed its integrity check. Failed file ingestions generate an alert with the failed file archive file information. The compute extract configuration data includes the data field that contains the date time value to use for time series purposes for each data source, which can default to the ingestion date if there isn't a specific or known reference date contained in the file, and also specifies the file format for each data source. The extraction process is to a file format type. That is, the same process is used for a given file format from any data source, and that process will extract and save all identifiable data points contained in the file, irrespective of whether those data points are referenced as required fields or as expected fields. If the file format is unstructured or semi-structured, it will extract all identifiable key value data points. The extraction process is run on ingested data that pass their data quality check. All identifiable data points in the ingested and QC'd file are appended in a structured Parquet data store with the date value as a column to enable time series analysis. The compute curate configuration data contain the parameters needed to enable the presentation layer, primarily the data inputs for each use case, any required data type passed in, and any downstream calculations for derived output values. The curation process pulls, casts, calculates, and orders data points from the structured data store according to those configuration parameters, and saves the results to the curated Parquet data store. A query engine, which is Redshift Spectrum in our reference project, points to the curated data store and is connected to visualization tools such as Tableau and MicroStrategy, in which interactive reports can be built to track each use case. And some last words on data governance and security before we wrap up the presentation and move on to Q&A. All data storage and computing resources that make up the platform are part of the client's cloud infrastructure. And as such, proper security and governance is accomplished effectively by piggybacking on the established best practices for the cloud infrastructure service. So in AWS, that means all resources are stood up behind a virtual private cloud with a VPN tunnel connecting it to the client's internal network. IAM policies and roles are created to limit permissions on each data source to its intended audiences and/or resources. And one landing bucket per data vendor or source is established with proper security policies applied to limit access to its respective data provider and the ingestion process. So, in other words, the separate buckets per provider is to prevent each provider from being able to see anything that the client may be receiving from the other data vendors, even though the data is transitory in the landing bucket and is removed by the ingestion process shortly after its delivery. So let's wrap up the presentation with some key takeaways. So our cloud-based modular architecture allows for dynamic vertical and horizontal scaling. Its configuration-driven platform enables rapid addition and modification of data sources and use cases with no modification to the platform code base. The universal extraction process for each file format allows for rapid onboarding of new data sources, data discovery, and the richest possible data set for the data laboratory. And the configurable curated data store with a cloud-based query engine provides a flexible interface to a wide array of data visualization tools. And I think we're ready for the Q&A part now.
All right, Robert, thank you so much. Like Robert said, for any questions that you guys would like to ask Robert, please enter them in the questions panel on your right, and we will answer them in turn. If we do not get to them, we will definitely answer them via email. So let's get started. Question number one. Yes, this is a cloud-based platform, but does it need to be in the cloud? What if my firm is not? Is this still possible?
So the short answer is yes, but there is a but. So the primary benefit to having it in the cloud is the ability to scale up and down your computing resources as needed. So you certainly could build out all this functionality using in-house resources, provided you have the computing capacity. So if you can run a Spark cluster that can ramp up enough nodes to accommodate your largest inbound data flows, then sure. Or for that matter, if your resources can accommodate the types of potential machine learning use cases you may want to be doing on your data set, then yes, of course.
Okay. So I'll jump into a machine learning question because it ties into that. In this architectural platform, where would machine learning fit in to build the models?
Sure. So the structured data store is basically, it's a Parquet data store, which is columnar, and the data scientists can interact with that data using Databricks PySpark notebooks. So basically, what that notebook gives them, they can write in PySpark, or Scala is another option. But between PySpark and R, they really have all of the standard machine learning functionality you would want. PySpark has MLlib, which is, it contains effectively anything you would probably ever think of using. And again, because it's on Databricks, you have an auto-scaling Spark cluster sitting behind it, so you can accommodate pretty much any level of computing resource application you might need.
Okay, thanks. Here we have one about pricing. What is your recommendation for managing costs due to data access and scaling factor?
Well, in Databricks specifically, although other Databricks needn't be used, there are equivalent functionalities you could build yourself. But with Databricks, you can set maximum limits for your cluster size. So one nice thing is, first of all, it allows you to use spot instances. So for your cluster, so that can keep costs down. But I would say the primary way would be to just put hard upper limits on how high your scaling can go, cluster size wise. So, for example, you wouldn't want a data scientist to inadvertently run some massively intensive exercise on the data set that runs up a large bill. Again, using spot instances, though, it's becoming harder and harder to rack up enormous bills, but that's certainly not to say it isn't impossible.
All right. We have a question on how many hedge funds or funds in general have already similar infrastructures in your view? I'll actually take that. We're not saying that this is the only architecture, or that, and we're actually not sure how many others out there are using this. But this is one that we architected and we built to be as effective as possible in leveraging alternative data. So if you'd like to contact us about this architecture, we could tell you more and give you more insights and why we did it. So I'll go on to one more. What is the average volume of feeds or sources taken either daily or monthly? monthly? And what is the time taken from ingestion to curation?
So I didn't hear the first part very clearly. I'll address the second part, and then we can circle back to the first part. So the ingestion time can basically, because this is scalable, basically your need for speed is balanced with how much computing resource you want to put behind it. That's really one of the key strengths of this architecture is if you just want it chugging along at a low baseline, and you don't mind that if you're hit with an enormous amount of source data, it might take a while to chug through. You can keep your cluster at a lower baseline operating size. On the other hand, if you want to ingest any amount of data in the quickest amount of time possible, this architecture really allows for that. So in essence, you're starting to get into the maximum theoretical limit of ingestion really just comes down to the limits of how well PySpark can break up and parallelize the ingestion process. And it's generally pretty effective at doing it, but there are, of course, some just mathematical upper limits involved there.
All right. And with this specific architecture, the question was also asked, what is the average volume of feed or feed sources, and either taken daily or monthly?
Oh, okay. So let's see. With this particular reference project, but when I walked off the project and it was transitioned primarily to in-house people, I think we were at something like 6 different data sources, one of which was quite a lot of data. Actually, the challenge was that it was an enormous number of small data files, which present kind of a unique challenge with regards to, sometimes it's easier to process one enormous file than tens of thousands of smaller files. But again, this architecture can perform pretty much equally well on both types. I know they had a roadmap to onboard several others, but yeah, it was roughly 6. I would say in terms of I would say it was ingesting somewhere in the maybe hundreds of gigabytes of data per month. It was more the data sources weren't such that you had tens of thousands of individual attributes. It was the challenges were really being able to perform discovery and make sense of the metrics, and then contextualize those desired attributes and bring them out in the curated layer, which was really what this platform excels at.
All right. Thank you so much, Robert. That's all the time we have for questions today. If you'd like to ask a question, you can feel free to email me to remy@caserta.com. Thank you again for coming, and the recording will be your way shortly.